Okay, so continuing on from our previous video, we're going to look at how we can get expressions to let us be able to actually calculate fugacities and get numbers, right? Not just like this theoretical idea, but get actual values. So let's look at first at delta G2. Delta G bar 2, for both of these, we're looking at a change in pressure, right? We've decreased the pressure to this theoretical, low pressure, whatever, low, right? We don't need a specific number here, actually. And if we want to know delta G, well, we integrate from P to P approaching 0. We're changing the pressure, and we'll integrate dG bar dP at constant T. We're keeping the temperature constant. And that should be dP. So that means that our value of G bar is going to be, we're going to make the substitution that this is equal to V bar, and we're integrating over P prime. Okay, that's about as far as we can go here, because what the actual value of V bar is, this is the gas is following real gas behavior under these conditions, right? We have not gotten to ideal yet. Okay, so we'll stop there. What about delta G3? Well, we're going to have a similar sort of expression, but now the gas is behaving ideally the entire time. So we have this low pressure up to P. We have V bar ideal as P is changing. And I'm writing P prime, which I probably should have done up here too, to differentiate the fact that our starting P value here is a specific pressure, but we're integrating over the pressure variable, just to mathematically keep track of this. Okay, and now because this is ideal, we can go ahead and make the substitution that we have RT over P, because this does behave ideally. We are assuming ideal behavior for this theoretical process. Okay, so then we can go ahead and combine, right? We know that delta G bar 1 is equal to the sum of delta G bar 2 and delta G bar 3. Okay, so we can go ahead and do an integral here, or add these integrals together. So we have the integral from P to P naught of V bar dP prime, plus the integral from P0 up P low pressure to high pressure of RT over P dP. Not ddP, just one P. Okay, so we've got an expression here. Now we'd like these integrals to go in the same direction. So we'll swap the limits on the first integral. All right, so if we swap the limits, we have to put a negative sign in front of it, but otherwise it's the same. So we'll go from P0 up to P, V bar dP prime, plus same limits. All right, and now that we have these with the same limits, we can combine what's inside of the integrals. Whoops. Right, and we'll call this, once we do that, we'll call this equation 2. So the integral from low pressure to high pressure of RT over P prime minus V bar dP prime. Right, so now we've combined this into one expression, and you can sort of see how this is the difference between an ideal behavior versus the non-ideal behavior, whatever V bar we have. Okay, now this is a second way of expressing delta G1, delta G bar 1. So we can say these are equal to each other, right? So our initial expression was RT log P over F, right? That was our our first expression for delta G bar 1. This is this imaginary process of going from the real gas to the ideal gas at the same temperature and pressure, and that is equal to this integral. And what's useful about this equation is that everything on the right-hand side of the equation is all just temperatures and pressures and molar volumes. And so if you can measure molar volume as a function of temperature and pressure, you can solve this integral. You can numerically get values for this integral. And then what's on the right then, that allows you to solve, if you know all of those things, you can then solve for the fugacity. And so this gives you a way of actually calculating fugacities. So in the next video, we're going to look at this expression and what you would need to do to be able to use this.